So in the course outline, right? So we are in the last topic today. So hopefully, we'll finish it today, both the theory as well as the practical sessions. All right. So this concludes the teaching part of it. And then next week onwards, you have to present your project report, and also you have to do your group presentations. So how far you are in that line? I haven't received any groups. I got only one group, all right, but no topics given. So I want you to guys to be more focused on that. I given the freedom of choosing your own group, and also I given you the descriptions. What are the contents should be included there. So you can have on an average 5 persons in one group, and then if there is any odd numbers comes, you can have 6 people, right? Depends on the number of groups you have. If any extra person, they can be accommodated in any one of those groups. So maximum you can have 6 persons, right, in one group. And as I said earlier, so each person should take turn in terms of presenting the project. And when it comes to the data analysis part, everyone should take a turn and present some of the tools that you have used to analyze the data, right? On the how you draw the conclusions and so on. Okay, the interpretations.
Good afternoon, sir. Omar here. But I don't think, at least our group won't be fully prepared to present next week. I'm not sure if any other group will be ready to present as early as next week. We need, maybe the following week we can present.
So you need one more week to prepare, or okay, let's say let us make it this way, right? So next week Monday, what you can do is you can introduce your group members, right? And what is your project title, right? So that you can present and what are the things you're going to do and all that, just briefly. But perhaps in the following week, you can start do your report, and also simultaneously you can do your presentation. Is that sounds good?
That's okay, yeah.
So choose a topic which is very relevant to your area. But when it comes to the statistical data analysis, use all the modules that you learned, right? The 7 modules that we have focused on so far. So use all the modules and draw the conclusions, okay? So you effectively do your models. Not necessarily all the, you can choose one technique, right? For example, mean, median, mode, all will come in one technique. You can use some graphs, and then one-way ANOVA, two-way ANOVA, and then try to do a logistic regression and a multiple linear regression, all right? Put a correlation there, and then independent sample t-test, like that. So your data must have the room for all these tools to be accommodated. And also, of course, I'm going to teach something interesting, a non-parametric test today, okay? So these tools also should be incorporated into your report, as well as the data analysis part, right? Your project report outline should contain all those 15 areas should be covered, okay? So is that clear, everybody? So why we need to go for non-parametric tests, right? So you remember that when we are doing the parametric, means the one sample t-test, independent sample t-test, paired sample t-test, one-way ANOVA and two-way ANOVA. So these are all parametric tests. Why means we are testing the parameters. In all these cases, in one sample t-test, we compare the mean equal to a specific value, right? So what is the average income? So the average income of Guyanese is equals to $50,000. So that mu, the population mean income, right? That 50,000. So that's what we are testing, right? In that particular case. So when it comes to the independent sample t-test, we are comparing the difference of the two population means, mu1 minus mu2, or mu1 is equals to mu2. And when it comes to the paired sample t-test, so the before and after, right? So the average, the before the exercise is same as the average weight after the exercise, okay? So there also we are comparing the two means. And then the one-way ANOVA, we are comparing more than 2 means, okay? So whenever you're comparing more than 2 means, right? 2 or more than 2 means, we embark on the one-way ANOVA, and then the same way we go for the two-way ANOVA, but you have the block and treatment approach, okay? So all these parametric tests, so we had that basic assumption that your sample should follow the normal distribution. Okay, so that is the fundamental assumption, right? The distributional assumption that we have, that your sample, whatever the sample that you're selecting, should follow the normal distribution. But whenever there is a theory that whenever you have a sufficiently large sample size, right, then this will follow, the sample should follow the population, the normal population. That's how we used all the assumptions. But there are some situations where the normality fails. So if the normality assumption fail, then what do you have to do? All right. So that's where the non-parametric tests established. Hepzibah, is that clear?
Yes, sir. Thank you.
Okay. Yeah. So when the normality assumption fails, right? So what we have to do? So that's what we are into this non-parametric test. It's very useful, right? Whenever you have a survey, these non-parametric tests are very useful in order to formulate and identify which, see, for example, which newspaper is popular, right? If you wanted to know that you have 4 or 5 new dailies in newspapers, and you want to know which newspaper is very popular among the public, right? The readers, regular readers, and then which is the movie is most popular, and which cricketer is highly rated. All that you can do with the non-parametric test. There are so many tests are available, and we will see some specific tests and the purpose of it. Okay, so that is the main essence of this particular session. Collected a sample, and that sample you're testing for the normality assumptions, like drawing a box plots or drawing a histogram or PP plot, all that, and you come to a conclusion that this particular sample is not following the normal distribution. So you cannot do any t-test or ANOVA and stuffs like that, because for those tests, those parametric tests, the basic assumption is that your sample should follow the normal distribution. Okay, if that fails, then you need to have some alternative. Okay, so these non-parametric tests are the alternatives to a sample when it does not follow the normal distribution. Okay, whenever the normality assumption fails, then you can embark on these non-parametric tests. Okay, so that is the main idea of this lesson. Okay, so are most variables are normally distributed? Okay, so in the above example, you retired on your knowledge that it repeated samples of equal size, the means will be distributed following the t-distribution, most approximated, or the normal distribution. Okay, so in real life situations, so many of the variables may not be normally distributed. Suppose if you're doing some qualitative analysis, right? So there, the normality assumption may not be that possible. Okay, even in the medical field, okay, the incidence rate of rare diseases are not distributed normally in the population. Okay, so for example, this COVID, this new pandemic has evolved. We have a population of 760,000, okay, but so far 6,000 cases, almost close to 7,000 cases confirmed, and the number of deaths is like 160, 170, that range, right? So there are a lot of recoveries also. So when you look into all this information, they may not have the normality assumption there, right? So and the number of car accidents is also not normally distributed, and there are many other variables in which a researcher might be interested. Okay, so in qualitative research, there are so many areas where you can find variables, but they may not follow the normal distribution assumption. Okay, so and also the sample size also a factor. So another factor is that often limits the applicability of tests based on the assumption that sampling distribution is normal is the size of the sample of the data available for the analysis. So what is the sample size that you have, right? In most of the medical research, you may not have that number of samples. So, if you look into that the medical data, right? Because medical data is, for example, if you want to do some research on HIV and AIDS, or cancer patients, right? So not many people, because of the taboo and the sensitiveness and all that, and people might think that even COVID also, because the moment the people tested positive, what happens? They follow their discriminatory procedures. Okay, so people don't talk to them, don't touch them, and don't associate with them. You put them in quarantine, right? So because of so many reasons, they don't come forward and tell that they are infected with certain diseases. Okay, especially if it is communicable diseases, they don't come forward and tell, because people might follow the discriminatory procedures and stuff like that. So if you are embarked on such kind of research, so the sample size you need to work with might be, let's say 10 samples and like that. So if you are working with the small samples, right, so you may not get a good inference out of it. So that is why the non-parametric test is an alternative approach where you can do your things. There in non-parametric, you may not have a distributional assumptions. You don't have any distributional assumption. It's a distribution free, right? You don't have any distributional assumption there, and also you can work with small sample. Okay, so that is one advantage of non-parametric tests. So the problems in measurement, most common statistical techniques such as analysis of variance, regression, etc., assume that the underlying measurements are least of interval quality, meaning that equally spaced intervals on the scale can be compared in a meaningful manner, like a B minus A is equal to D minus C. So however, as an example, this assumption very often not tenable, okay? And the data rather represent rank ordering of information, ordinal scale rather than precise measurements. So what does that mean? Means, so when you're doing analysis of variance, t-test, regression, and all that, you need to have a quantitative data, right? You have a measurements like height, weight, blood pressure, and oxygen, carbon dioxide emission, right? If you're involved in pollution, right? And rainfall data. So all these measurements have all these variables have some kind of measurements, right? And if you wanted to do these analysis, but sometimes in real time, right, you might need to for some rank ordering. For example, some ordinal scale. See, for example, if you wanted to know what is the satisfaction level of a certain organization or a hospital, right? If you work in a hospital, the patients might need to want to know that what is the level of satisfaction, right? That hospital is providing. Are you very much satisfied, not satisfied, not at all satisfied? So this kind of ordinal scales, you might involve in the rank ordering. Okay, so you cannot expect those variables follow they don't have any measurements, right? Rank ordering, you just rank ordering, right? 1, 2, 3, 4, like that. There is no measurement is involved. That is the meaning of it, right? There is no precise measurements in rank ordering. Whenever, especially if you do some survey or if you do some marketing research, so there is no precise rank ordering. If you doing some qualitative research, we'll see today some of the examples there, right? So in parametric approach, you have measurements there, right? You have measurements there, but in some cases you may not have that measurements, but you cannot. So those variables need not follow the normality assumptions. Okay, so that is why we need to go for some non-parametric tests. So the brief overview of the non-parametric procedures, the tests are different between groups, like independent samples. You can compare two independent group samples, and also you can compare a difference between variables. You can compare two different variables, and also you can compare the test of relationship between variables. Okay, you can compare the test of relationship between variables. Okay, so all these comparisons you can do with the non-parametric tests. And there are a lot of the procedures are available, so we'll see one by one. Okay, so what are the advantages of the non-parametric tests? So the non-parametric tests are distribution free, as I said, whereas in parametric test you have a basic assumption that the sample should follow the normal distribution. Okay, but in non-parametric test you don't have such distributional assumption. You can apply it, right? They do not require any assumption to be made about the population following a normal or any other distribution. So you don't have any underlying distributional conditional here, right? So there is no baseline distribution assumption here. So the sample, we don't check the distribution of the sample, right? You can directly apply the techniques. So generally they are simple to understand and easy to apply when the sample sizes are small. Okay, you can easily apply it. So most non-parametric tests do not require lengthy and uh, laborious computations, and hence are less time consuming. If significant results are obtained, no further work is necessary. Okay, so that is one thing. Like see, for example, in ANOVA, right? So if the test says there is a significant difference, then we go for further analysis like a multiple comparisons and so on. Okay, but here we don't have such. Once the test shows that there is a significant difference among the groups or between the variables, right? So then we stop there, right? And then non-parametric tests are applicable to all types of data. Like as I mentioned, it is whereas parametric test, we can't do for nominal, ordinal, and scaling, right? Like whenever you follow into a group, like now what is a religion or what is ethnicity? So if I ask, that is a nominal questions, and how do you rate the services provided in a Giftland mall, right? So these are all some of the qualitative type of information data, but you cannot apply this in parametric setup, right? But in the non-parametric setup, you can analyze all this data in a rank form, ordinary scaling, as well as data that have been measured more precisely, interval or ratio scaling. So many non-parametric methods make it possible to work with a very small samples. As I mentioned earlier, whenever you might have a situation where you have to deal with a very small sample size, right? So in that situation, the non-parametric tests are useful to analyze the data. So this is particularly helpful to the researcher collecting pilot study data, or to the medical researcher working with a rare disease. Okay, so whenever you're working with a rare disease, and if you want to do a pilot survey with a small sample, right? You wanted to do a survey, right? And you have tested the questionnaire and all that, and you wanted to test the reliability and validity of that questionnaire, then you wanted to embark on a small pilot study, right? So in that case, you can use the non-parametric tests to analyze the data. And then the other thing is that the non-parametric methods make fewer or less stringent assumptions that are most easily met than do the classical procedures. Okay, so the very few assumptions are there, right? Unless if you look at the parametrics, right? So in some cases, you need to have equal variances assumption. If you want to do ANOVA, you always test for the equal variances, and also you have an assumption of independent sample t-test. There also you need to have an equal variances assumption, all right? And the sample, besides that, the sample should follow the normal distribution, and a lot of no conditions are there, right? But here, you don't have much of those conditions, right? So it's very widely popular and more useful, widely used ones. Some of the tests that we are going to do here is the large number of non-parametric tests exist. There are so many tests are there, but in this module we will discuss only a few of the better known and more widely used ones. They are the two-way contingency table analysis, which we use the chi-square test. Chi-square test we use it, and then the Mann-Whitney U test, and the Kruskal-Wallis or H test, and then Cochrane's Q test, and then Kendall's W test, and Friedman's test. Okay, so these are the six tests that we are going to do in this module. Okay, they're very popular ones, and they have a special purpose for that. So first, let us start with a two-way contingency table, right, and also called association of attributes. Like a contingency table is like so when we are comparing two attributes, right, two variables you want to compare, then that is the two-way contingency. You remember that we did a two-way table cross tabulation. Let me take you the two-way contingency tables. So basically, it compares. The hypothesis is that there is no association between the two phenomena, right, or the two attributes you have. And then the alternative is that no, there is an association between the two attributes or between the two phenomena. Okay, so you have a column variable and you have a row variable. Okay, and you have a frequencies for that. Okay, and we check for is there any association or is there any relationship, right, between those two variables. So that's what we do in a two-way contingency table. Of course, you'll have done it in a theoretical way. Just open the data, the SPSS data, then the diabetic data initially in the beginning, I sent you to do some analysis. Okay, so you can open the data. Okay, so you have the data, right, everybody? Okay, so now tell me which are the two variables you can compare. The two attributes, right? You can identify. I want to know whether there is any relationship between the gender and on the years they have diagnosed with a with a disease, diabetic. Does it make sense? So, is there any association or relationship between the gender and the year in which they are diagnosed with the disease? Will that make sense?
Or maybe better to check the ethnicity against the diagnosis?
No. The gender of a patient, that means the sex, right? Male or female, versus how far, how early they are diagnosed with the disease. So the diagnosed, right? So you look at the variable list. So you have the diagnosed here. When was your diagnosed, right? So you see less than or equal to 5 years, 2 is 6 to 10 years, 3 is 11 to 15 years, and 4 is more than 15 years. Okay, so when their diabetic was diagnosed versus the gender of the patient, will there be a good comparison? I'm asking.
I don't think so, sir. I don't think so. I don't think that's a good comparison.
Gender will not make a comparison. Okay, so what else will? No, I just want to see. I don't know whether it is a good comparison or not, but I just wanted to see as a researcher whether the gender will have any relationship with the time at which they are diagnosed with the disease.
It would help without analysis, yeah.
I just want to find out, right? I just want to find out. I'm not saying whether it is a good analysis or not, right? I just want to see whether there is any relationship between these two. That's my idea, right? So if at all, you can take any two variables, but see that it will make any I wouldn't say it's a sense. Sometimes it may be spurious also, right? So according to this data, right, I just want to make a small comparison like that. So now you go to analyze, right? Analyze, and then you go to descriptive statistics. So statistics, right? So go to analyze. Use crosstabs, right? Click crosstabs. So use gender here, right? Gender, and then when was your diabetic was diagnosed, right? When was your diabetic was? Put that into the column, okay? And then go to statistics. The click chi-square there, right? Click chi-square at the top. Click chi-square at the top, and then click continue. And then cells you have observed, right? The counts. Observed means what is observed from the data, from the survey, right? What is observed from the survey. And then the percentages, you can click the percentage of each area. So you can click that row, right? Percentage. Click row percentage. And then click continue, right? And then click OK. Click OK. So you are getting this output?
Yes, sir.
Yeah, okay. So what? Okay.
Can you go over for me, please?
Pardon?
Can you kindly go over for me, please?
Okay, no problem.
Analyze.
Yeah. You have the data, right? Open the data. Right? So click analyze, and then descriptive statistics, right? Click cross tabs, okay? Click cross tabs. So you reset, right? And you have this the gender, right? Gender, I put it in the row, okay? Click it in the row, and then when was your diabetes diagnosed, right? When was your diabetes diagnosed? So I put there here. And then Then click statistics, click statistics, click chi-square, right? Top, chi-square, and then click continue, okay? Click continue, and then go to cells, observed is there in the counts, observed, right? That's observed means what you're getting from the data, right? The sample that you collected through the survey. So that's what is the observed meaning. Then you calculate the percentage, right? You calculate the percentage. So that is the row percentages, right? You click that and then click continue and then click OK. So you have this data. So there are 114 samples here, right? And then 100%, there is no missing data here, right? So everything's fine. So now you look at this one here, the male. So the male, among the males, so there are 33 non, and then female is 81. Okay, so that itself is a disparity. The samples which they collected. Okay, so predominantly, they went to a clinic where a lot of female patients. Okay, this distribution is also a lot of biased. Okay, that's fine, but just for understanding purpose. Okay, so from the 33, right? This 33. So you see 8. So that means 24.2% of the male are diagnosed less than or equal to 5 years. Okay, less than or equal to 5 years. And 9.1% 6 to 10 years, and 21.2% are 11 to 15 years before they're diagnosed. And then 45%, right? They are more than 15 years, right? So the male, more than 15 years, they are diagnosed, 45.5%. That's the high rate. If you look at the female, right? So 38.3% is less than 5 years, and then 29.6% is 6 to 10 years, and then 11 to 15% is 17.3%, and more than 15 years is 14.8. Okay, so there is a lot of variations in that thing. So now our main interest is that, as I said earlier, my hypothesis is that there is no association or relationship between gender and when the patient was diagnosed, when they were first diagnosed with the diabetes, right? How many years ago? So my hypothesis is that there is no association between gender and the year or the when they were first diagnosed with diabetes. Okay, when they were first diagnosed with diabetes. That is my hypothesis. And my alternative is that there is an association. There is an association between gender and the time in which they are first diagnosed with the diabetes. Okay, so that is my hypothesis on the alternative, right? So I'm looking at the Pearson chi-square here. There are other values, but mainly focus on the Pearson chi-square. So which is 0.002. Okay, 0.002. So which is less than 0.05, right? 0.05. Therefore, we conclude that there is an association between gender and the time in which they are diagnosed with the diabetes. Okay, the diagnosed with the diabetes. Because I agree with that, because male, they even though they show some symptoms, they sometimes they might afraid, or they don't want to go and check their blood glucose or the blood pressure or anything, right? If they have any symptoms, anything, they're very reluctant to go to the doctors and check. All right, but females, they give more care in that. That could be the one reason, they see you see the percentage, right? So you see more than 15 years, this 45.5% they're diagnosed earlier. Here is 14.8%. So here, this is the variation here. Less than 10 years, you almost have 38 plus 29, so almost 70%, close to 70% of the female are diagnosed before the 10 years, all right? But men, they are diagnosed more later. So 45 plus 20, so 66%, like between the 11 to 15 years age. Right? So that is one of the perception. That is that's I'm suggesting that. But the report says, the analysis says that there is an association between gender and the time when they were first diagnosed with the diabetes. Okay. So like that, I want you to do look at the data and you see, show one example for me, right? Everybody. So independently you do some, see you have the data, right? You have the data and also I have sent you the questionnaire, isn't it? Yeah, so pick two variables, right? Pick two variables and compare. Use the chi-square test and do the comparison. Do it as an exercise, quick. Can somebody present your work? Okay, good, yeah. We can do that. So show it, you want to share the screen? Okay. Yes, Masha, go ahead. I give the access.
Hi, this is my result. Should I go back how I got it?
Yeah, just show them, how you got it and
Okay, so
the variables that you took, right? Yeah, for comparison.
okay, so this is the general data. I went to analyze.
Yeah, go ahead. Yes.
Analyze. From analyze, I went into crosstabs, and I selected gender as the row, and how often you consume fast food. So that's somewhere till down at the bottom here. Yep. One something here. And went into statistics and selected chi-square. Chi-square, sorry. Continue, and then cells, observe, and rows.
Yeah.
And I could continue. And then from here I could OK.
Yeah.
So after I did that, then I got the results here.
Okay.
The summary and the gender versus
okay. So what is the hypothesis here? You have to mention your hypothesis.
So I was thinking there may be a relationship between gender, male and female, and how often each may consume fast food.
No, the hypothesis. No, hypothesis should be no difference, right? There is no relationship. Yeah, there is no relationship between gender and how often they consume fast food. Okay. That is a hypothesis. And the alternative is there is an association between gender and how often they eat fast food. Right? So, yeah. Go ahead. Yes. And you can pick highest percentages, like for example 66.7% that you can include for your analysis. So among the males, 66.7% of the males, they do not eat at all. They do not eat fast food.
They don't eat.
Yeah. They do not eat at all, right? And when it comes to the female, almost 60%, because they're all diabetic patients. So they might have some idea about the fast food. So 60.5% of the females, they do not eat at all, right? Yeah, so those two are the major percentages. So you can take that and you can bring it in your analysis. You can mention it, right, in the report. Yeah, good.
And the chi-square test, the Pearson chi-square. I notice that's more than the 0.005.
That means, yeah, that means
that the hypothesis would be
is insignificant. Yes, yeah, because 0.555 is greater than 0.05. So you accept your hypothesis, right? That means there is no relationship. So gender and how often do you eat fast food? They are totally independent. Okay, so there is no association. There is no relationship. So if you're eating often fast food, it doesn't mean that you are a male or a female. Okay, that doesn't contribute whether you're eating fast food too often, right?
Okay, so this 0.555, that would mean that the hypothesis is
insignificant.
Insignificant.
Insignificant, because there is no association. There is no relationship.
General hypothesis would be that there's no relationship between gender and how often they eat fast food.
Yes.
And the alternative would be that there is a relationship.
Yes, right. And since the p-value is greater than 0.05, so we accept our null hypothesis. Okay, so therefore we can conclude that there is no relationship between gender and how often they eat fast food.
Okay, so this is accept. You said accept null hypothesis.
Yes, accept the null hypothesis. Yes.
I started to understand it better now. Thanks.
Okay. Yeah.
So the likelihood ratio, and we don't.
No, mainly we look into that Pearson chi-square value. Pearson chi-square. Okay. So likelihood ratio is also kind of a comparison, but mainly we look into that Pearson chi-square value. So that is the p-value that we refer to.
Okay, sorry.
Don't worry about the other things. Mainly look into that Pearson chi-square. Right. So see that value is more than the standard procedure only. Hypothesis always a standard procedures. So if the p-value is more than the level of significance alpha, which is 0.05, right? So if that is more than 0.05, you always accept your hypothesis. Okay, and if it is less than that, you reject. So since we made the assumption hypothesis that there is no relationship between gender and how often do you eat fast food, right? So we accept our null hypothesis and we conclude that there is no relationship between these two variables.
Okay.
Is that clear? Yeah.
Yes, sir.
Okay, good. So any other volunteers? You have picked any other combination of variables and you want to demonstrate that?
Yes, sir. I could share mine.
Okay, do that, please. So first explain which are the two variables that you picked for the analysis, and how to do, what is your hypothesis and what is your alternative, and you explain some of the percentages, and also you can do the thing, right? Yeah, go ahead. I think you are comparing age and what? When was your
Age and when you're diabetic.
No. See, the age is here. Here, the age is a quantitative variable, right? It's number. You understand? So this is the chi-square test. You have to use it when you are comparing two attributes, right? Or two phenomenon. So here age is measured, right? It's in years. So if it is in group, I agree. If the age is put it in a group like 20 to 25 and then 26 to 30, like that, if it is grouped, then I agree with your thing. But here age is a numerical data. So that is why you are getting. Can you scroll down your table? The two-way contingency table.
Okay.
Yeah, just cancel it. Cancel here. Just cancel. Yeah, you see? Yeah, this is a problem. So you cannot make any. Yeah. So this is two attributes, right? So you cannot make anything. Anyway, the analysis will come, but no, it's we always compare with the two attributes, right? Attributes.
All right then. So ethnicity.
So that's why the numbers are not coming good. You can. You want, yeah, you can do ethnicity versus when was your diagnosis. Yeah, you can do that. Yes.
Okay. Okay, so it says.
So it says, the Afro-Ghanese, 34.3% of the Afro-Ghanese, they're diagnosed less than 5 years, and then there is 22.9% is 11 to 15 years, right? And 31.4% are more than 15 years. Okay, that's the thing. And when it comes to Indo-Guyanese, 33.9% is less than 5, and 32.3 is 6 to 10 years ago, and then 16 point is 11 to 15, and 17.7% is more than 15 years, right? Amerindian, yeah, 50%, and yeah, done. Portuguese, it's because it's only 3 sample, right? So you have, each one will give you 33.3% because there are only 3 samples. Okay. The others, it's just only 8, right? Yeah, so 50%. Okay, so you can take the major percentages and you can explain that. And then when it comes to the chi-square, right? So your hypothesis now, ethnicity, there is no relationship between hypothesis, right? There is no relationship between ethnicity.
No relationship between ethnicity and the
Yeah, when they
diabetes
first diagnosed
diagnosis.
with the diabetes, right? Um, and then
The
in the
alternative,
alternative, yes, yeah,
there is a relationship.
relationship between ethnicity and when was the first diagnosed with the diabetes. Okay, and yeah, so now go ahead with the Pearson chi-square. What it says.
0.275,
Uh-huh. So which is
and that is less than 0.
less than? Is it less than 0.275?
0.5 is what we're testing.
No, we are testing with
0.05.
0.05. Yes.
Okay, so this
Zero.
is greater than
Yeah.
the 0.05,
Yes.
and it's not significant.
Therefore, we accept our hypothesis.
Alternative.
No,
We accept
hypothesis.
or null
Accept our
hypothesis.
hypothesis, the null hypothesis, yes. Because this is the p-value, this is the p-value which is greater than 0.05. Therefore, we accept our null hypothesis. So therefore, we conclude that there is no significant relationship between ethnicity and when was they first diagnosed with the diabetic, right? The patient. Is it clear?
Yes, sir, it's clear.
Okay. Yeah. Okay, so then we can move on to the next tool, right? So this is the chi-square, right? Basically, you are testing the relationship between the two attributes. Yeah, there is no relation, correct. There is no relation between these two.
Before you move on, sir, just a quick question.
Uh-huh.
In relation to the 0.05 which the measurement was taken against, is this a rule in Pearson chi-square that this is
No,
the
in
number that you look for?
all the testing of hypothesis procedure. Even t-test also we did the same thing. T-test, ANOVA, all the testing of hypothesis procedures. You always compare the level of significance with the p-value, right? This is a standard procedure. So whenever the p-value is more than the level of significance, right? We accept our hypothesis. When the p-value is less than the level of significance, we reject the null hypothesis.
All right, thank you.
Yeah, so that's a standard procedure. Whichever the hypothesis testing problem you're doing, this is a standard condition, right? Yeah.
All right, thank you so much.